Now we will talk about the simple harmonic motion, but from a different perspective, which is the spring. So when we say spring, what we imagine is we have something that looks like this, more uniform. So it's like you have hard, usually it is a hard steel that is in a form like this, that that you are able to either compress it or expand it. Now each spring has something that it's called the coefficient of the spring. It's unique for each spring. The coefficient of the spring is known with letter K. And we have talked a bit about this, but let's talk more. So the coefficient of the spring is known as what is the force, is the ratio of the force that is needed to compress or to expand the spring by 1 meter. So from this, what do we get is that the units for the coefficient of the spring are newtons per meter. Okay. Now, Hooke was living at the same time that Newton was living and was alive and was doing all this laws that we have talked up to now, but they were not in a good relationship between each other. Hooke was always thinking that Newton was not as smart, let's say, as he was, and Hooke himself was very smart. However, he did a lot of work on spring, and what he found is that the force of the spring is negative kx, where k is the coefficient of the spring, and x is the compression or the expansion that we are doing in the relation to the free spring, like not having any mass or anything. So it is in compression or expansion that we are doing. So let's clarify this negative sign here and the x sign, and why is it negative and so on. So if we have a spring, either a vertical or horizontal spring, let's take a horizontal spring. So you have a horizontal spring that it looks like this. And this is the length that the spring has when you are not doing anything to it. It's a free length, the length of the spring as nothing is on it. Usually this is assigned with XO, so original length of the spring. And now what do we do is we take this spring and we expand it. So we expand it at this length here. Now the x that Hooke's law is talking about is the final minus initial, okay? It is always the change between the final and initial. Now, the vector sign of this x will be this one here. Okay, this will be the x that is represented to the Hooke's law. And now, on the other hand, what the force of the spring is opposite of of this stretching that is done here. And the magnitude of it is negative, or magnitude of it is kx. So if we are expanding the spring, then the force that the spring will experience, or we will experience from the spring, is in the opposite side. So the spring will have the tendency, as soon as we release it, to go to the equilibrium position. And if we compress the spring, then it has the tendency to go in the opposite direction. So when we have the spring, the same spring that we are now compressing, so we are making it less, then the x of the spring is this one here, which means that the force of the spring will be in the opposite direction. So this is, again, is telling us that, oh, we have a force that always have the tendency to go to the equilibrium position, because this was the equilibrium position. No stretching, no compressing. Okay, this was the equilibrium position. Now the graph of the force of the spring with the magnitude of the force of the spring and the magnitude of the displacement is a straight line, and the slope of this graph will give us what is the constant of the spring, and the units for it are newtons per meter. Okay. In a tire pressure gauge, the air in the tire pushes against the spring when the gauge is touched to the valve, but it doesn't matter. If the spring, this figure says here, but it doesn't really matter. If the spring constant, so K is 320 newtons per meter, and the bar indicates an extension of 2.0 centimeters, what is the force that the spring is applying here? Okay, so now, again, the meaning of this number that you see here at the constant of the spring is that you have to apply a force of 320 newtons in order to compress or expand the spring by 1 meter. In this case, what is happening is that the spring is compressed only 2 centimeters. So the very first thing that we'll do is we'll convert this on the meters. So this will be 2.0 times 10 to the power of -2 meters. You can say this, or you can say 0.02 meters, and then 0.02 meters. And then apply the Hooke's law that is saying that the magnitude of the spring is, of the force of the spring is Kx. So now we know that always the spring is exerting a force of that it's opposing what you are doing to the spring. So if you are compressing, then the force of the spring will have the tendency to expand. And if you are expanding, the force of the spring will have the tendency to compress it back to the equilibrium position. And what we are talking here is the magnitude of the spring. So the force of the spring will be 320 times 0.02. So the force of the spring is, in your calculator, what is it? 6.4 newtons. So this is the force that the spring is exerting when we are compressing it by 2 centimeters. And now, in which direction is it going? It's always opposite of what you are doing. If you are expanding, then we'll have a tendency to compress. If you are compressing, then we'll have the tendency to expand. Now we have a mass of 2.45 is hanged into a spring, and then it is stretched what is by this much? What is the spring constant of the spring? The spring constant, okay. Okay, so let's take this situation and then expand it a bit more. So let's suppose that we have a vertical spring that, first of all, there is nothing on it, no mass on it, no nothing on it, okay? So the spring is this one here. This is whatever the length that the spring has from the fabric. So someone has produced it, a fabric has produced it, most likely will be in China, but doesn't matter. This is the length that the spring will have as we hang it into a vertical wall. Now, what do? Is we hang a mass, any mass, on the spring, and we wait until the spring and the mass is reaching an equilibrium. Don't worry about the question now, because we will talk about it again. So now, in this situation where the object is reaching the equilibrium, so this is the equilibrium, what do we have is something like this. We have the force of gravity. Now, as you see here, from this x0, the spring is stretched, which means that the force of the spring will have the tendency to go in the opposite direction. If x is in this direction, the force of the spring will be on this direction, correct? Based on the Hooke's law. So the force of the spring will be on this direction. So what do we see in this case, since it is the equilibrium, is force net is equal to what? What is force net? Force net, since it is in equilibrium, is equal to 0. Great. But on the other hand, what do we have? Force net is the vectorial sum of all the forces that the object is experiencing. So from here, we can say that mg in magnitude is equal to kx. Okay? From here, we find whatever is that the question is asking us for. Is this clear? What we will do now is we will take this, this equilibrium position, or this object here, and we will expand it even further. Okay, mass m here. So let's see now what do we have in terms of the energy perspective. By expanding this even further from this equilibrium position here, what are we giving to the spring? What type of energy are we giving to the system? It's that type of potential that we call it elastic potential. Do you remember when we did the types of energy? So we said that it's a potential energy. The energy that we are giving here is elastic potential energy, or just simply elastic. And it is calculated as a 1/2 K, which is the constant of the spring, x squared, where x is how much are you either expanding or compressing the spring from the equilibrium position. So this is the x that we are talking here. Okay? When we release the spring now, what will happen with the mass? And I will just draw the mass here, not the spring, because I'm not a good drawer. So the mass will go to equilibrium. Okay? And then we'll go to a position on the top, like compress the spring. And then we'll go to equilibrium again. And then we'll go to the maximum stretch. So as you see here, what the object is doing, this is expanded into a timeline, but what the mass is doing, it's going from this position that we are at into going up, and then going down, and then going up, and then going down, and then going up, and then going down, which is a periodic motion. So, and what do we have here in terms of the force is the restoring force is the force of spring. And because we said that the force of spring is always opposing what we are doing. So when we are at this position at the highest, we can say the lowest point of the mass, then the force of the spring will be toward the equilibrium. When we are at the highest point of the object, then the force of the spring will be toward the equilibrium. So those two are the restoring force. Since we have the periodic motion, the object is moving up and down, and if there is no loss of energy anyhow from the either the heat that is produced or as a result of the spring expanding and compressing, or as a air resistance, as the effect of the air resistance, then the spring will keep moving up and down forever. So since we have a periodic motion, since we have the restoring force, which is the force of the spring as a result of compression or expansion of the spring, it's always toward the equilibrium, then we can say that even the spring, it completes a simple harmonic motion. The two conditions to have simple harmonic motions are periodic motion and to have a restoring force that is toward the equilibrium. So since those two conditions are completed, then we can say that simple harmonic motion, that the spring is completing a simple harmonic motion. Does this make sense? So now, this potential energy, which we call it elastic potential energy, you can say potential energy, it doesn't really matter. That the system has accumulated here, what is happening is going, this is the maximum that the system may have. What is happening is transforming now based on the conservation law of energies, it's transforming now in a different type of energy. So we said that conservation law of energy in an isolated system is not destroyed, not created, but it is transformed from one form to the other. What form is it transformed at? As the mass is moving from this position, I will say the lowest position, to the equilibrium. So when it reaches the equilibrium, what type of energy is it transformed at the equilibrium on the chart? So what is happening here is that from elastic potential energy is transformed into kinetic energy, okay? Kinetic, and this is the maximum kinetic energy. Now you may say that, well, why not gravitational potential energy? The change on gravitational potential energy is so small, so it's safe to neglect it. And even when this makes sense, especially when you have a spring that is in the horizontal surface, then you will notice that there is no change of kinetic energy as gravitational potential energy as you are moving the spring left or right from the equilibrium position. And now, as of the mass is moving from the equilibrium to the highest point here, what is the transformation of the energy? What is transformation done here? What is happening? What is this maximum kinetic energy or the mechanical energy of the system transformed to? Yeah, so it's transformed into elastic potential, which is 1/2 kx squared. Now, since we said that we are having the same distance, x here and x here as well, this is the same elastic potential energy that the object has at the lowest position, and is equal to the maximum elastic potential energy. You cannot compress it even further, the spring, and it is equal to the mechanical energy of the system. So in the point that is in between from the lowest point to the equilibrium, and from the equilibrium to the highest point, we have both. On those points here, we have both kinetic and elastic potential energy. Now, for simplicity, I will just say elastic. Is this clear? It's the same logic as we did at the pendulum. So at the pendulum, we have gravitational potential and maximum kinetic at the equilibrium. And then in between, we have both. Now we have a maximum elastic at the maximum stretch and maximum kinetic at the equilibrium. And at the point in between, we have both kinetic and elastic potential. Let's bring back the question here. So we have a spring. The situational diagram is something like this. You have a spring that, let's not have the mass first, that has a length that is from the fabric, okay? And then what do we do here? We place a mass, and as a result of this, what is happening, a mass of 2.45 kilograms. As a result of this, the spring is stretched at 12.4 centimeters. Okay, and now we see that the spring is reaching the equilibrium. So the free body diagram will be force of gravity going down and force of spring that is opposite to what is happening to the spring. So you are stretching it, force of spring will have the tendency to compress it. Okay? Now, since it is the equilibrium, we said that force net is equal to 0. But on the other hand, what do we know about force net is vectorial sum of all the forces that the object is experiencing. So since those two forces are collinear, are on the same line or parallel to each other, then force of gravity is equal in magnitude to force of spring. Which brings us into, let's take this here, which brings us into mass times acceleration due to gravity is equal to k times x. On this relationship, we know what mass is, we know what g is, because we are assuming that we are doing this experiment at the surface of the Earth, and we know what x is. So let's find what k is, which will be mg over x. Use your calculator and tell me what k. You have it as 194 newtons per meter. Okay, so now we presented the formula for the period. Now, again, keep in mind what we are doing here. We are talking about a periodic motion, a simple harmonic motion, a motion that repeats itself over and over again. So now the period for the spring will be calculated as 2 pi square root m over k. Okay, you can see, you can find this formula in the formula sheet. Are you able to identify this formula? Good. And now we will talk again about the same logic. So when this is telling us, because 2 pi is a coefficient, this is telling us that period is direct proportion of the mass of the square root of mass. Square root of mass. So when you are increasing the mass, then the period is increased. But the factors will be, it's very similar to the length of the pendulum. When you are increasing it mass by a factor of 2, then period will be increased by a factor of √2 because mass is under the root sign. And when you are increasing the period, or sorry, the mass, when you are increasing the mass by a factor of 16, let's say, then the period is increased by the factor of √16, which is a factor of 4. Okay, and if you are decreasing the mass by a factor of 2, or let's say a factor of 3, then you are decreasing the period by a factor of √3, which is less than just 3. Or if you have a decrease of mass by a factor of, let's say, 25, then the period is decreased by a factor of √25, which is decreasing by a factor of 5. Okay, and the same logic as it goes for G, it goes for K here. So if you refer to the pendulum, you will use the same thing. Now, we have said again, even on the pendulum, that the period and the frequency are inverse of each other. And what is the period at the spring is the spring is going from one position, let's say from the lowest position to the equilibrium, to the highest position, going back to the equilibrium and coming to the original position. This is one revolution, one period, so the time that it goes from lowest to equilibrium, highest, equilibrium back to lowest is the period of the spring. Okay, so now what is the period of the vibrating spring with constant 100 newtons per meter? If a mass of this 500 grams, which means 0.500 kilograms, is hanged on the spring. So now the period will be 2 pi, the square root of 0.50 over 100. In your calculator, tell me what is the period. 0.44 seconds. Does that number represent? Is telling you that the time to go from, let's say, the lowest position to the equilibrium, to the highest position, back to the equilibrium, and then lowest position is 0.44 seconds. And if you are finding the frequency, then you go 1 over period, and that will give you that frequency. Now let's move to another example here. A 0.724 kilogram mass is oscillating on a horizontal frictionless surface attached to a spring with 8.21 newtons per meter. What is the mass displacement when its instantaneous acceleration is 4.11 meters per second to the left? Okay, think about this. Draw the situational diagram. So you will have a spring that goes like this. It is like this. You have an object here, and then you are, let's say, you are expanding this a bit, You're expanding this a bit in comparison to what it was, and then you are releasing. What is happening? The motion that the spring will have will be going from this, that is the X max, to the equilibrium. So we'll go from here to the equilibrium and then go compress the spring. This will be the same as the X max. And then we'll go back to the equilibrium, to this, and then back and forth. Now, what did we say about the restoring force? What is the restoring force here? Is the force of the spring. Guys? Yes? Yes? Okay. Because even if you do the free body diagram here, you will have force of gravity is, so if you do the free body diagram, you will have something like this. Force of gravity is going down. Force normal, since it is on a surface, is going up. Since the object is staying on the surface, those two forces are equal to each other. And the unbalanced force will be force of the spring. Force of the spring. So this is somewhere on the right of the mass from the equilibrium, the right on the side of the equilibrium. Okay, but it doesn't really matter, right or left doesn't really matter. So now what do we have is mass is equal to 0.724 kilograms. Coefficient of the spring is 8.21 newtons per meter. And now we are looking for what is X when acceleration is 4.11 meters per second squared. Now, we know that force of the spring is equal to force net. It's unbalanced force. It's the restoring force. Okay, based on the second law of Newton, this is equal to mass times acceleration, force net. So Kx, the magnitude of the force of the spring, is equal to mass times acceleration. So from here, we can say that X is equal to ma over K, or 0.724 times 4.11 over, what is it, 8.21. So X will be, in your calculator, 0.36 meters. Does this make sense, guys? Understand? Okay, so now we have a mass of 0.40 kilograms. It is vibrating, completing a simple harmonic motion in a horizontal spring along a frictionless surface, meaning that you are dealing with an isolated system. If the spring force constant, K, is 55 newtons per meter, what is, and the maximum displacement, which is known in the other words as the amplitude, X max, is equal to 15 centimeters. What is the maximum speed of the mass as it is passing through the equilibrium position? Okay, so we talked about this. Where is the maximum speed reached? At which point on the system? So the maximum speed is reached at the equilibrium. Okay, what is this then? Even if we don't know where is it reached, based on the conservation law of energy, we can figure it out. Where is it reached? So mechanical energy of the system is when we are expanding, we are expanding it. Yeah, we are expanding it at 15 centimeters is equal to the elastic potential energy, maximum elastic potential energy. And this is equal to 1/2 K of the spring, because we are dealing with the spring, X maximum squared. So now the mechanical energy of the system will be 1/2 times K is 55, and then 15 centimeters will be 0.15 meters squared. Now in your calculator, tell me what you should have. 0.61875, and I'm carrying all the digits. Yeah, good. Now, what is happening in the spring is the elastic potential energy of the spring is transformed into kinetic, and then elastic, and then maximum elastic, maximum kinetic, and then any point in between, we have both. So now in this case, the mechanical energy of the system, the 0.61587 whatever, is equal to 0.61875 joules, is equal to the kinetic energy, which is 1/2 mv max squared. We do know what is mass. And then let's find what is the maximum velocity. So from the formula, or from manipulating this, will be the square root of 2 times 0.61875 over the mass, that is, I think, 0.4. In your calculator, figure out what is, so you should have 0.76 meters per second. Okay, do you have any question on this? Those are the practice questions. The first two are simply spring, and the rest are spring and pendulum combined, where most likely you will use the conservation law of energy, or you will see it from the energy perspective. Work on those questions now.